developed clear and periodic waves, and you can best appreciate them by comparing them with the data he acquired solar wind, which essentially shows nothing or very small
activity.
It's a
spectacular difference, yeah.
Here you have really these strongly nonlinear already, with also superimposed high-frequency waves, which are probably due to some complicated interactions.
But when you say high frequency, they're still very long wavelengths.
Yes, there are, again, these several thousand kilometer wavelengths. And
they are produced by the picking up of water into the solar wind stream.
Yes, they are produced by the ions, produced by ionization of cometary material, and the free energy of these particles is then going into the generation of these waves, like in some, let's say, traveling wave tubes or so. In electric engineering.
Right, that's fantastic. Fritz, thank you very much. Can we come back to your waves later on? I did hear in my headphone, I don't know if anyone can confirm it, that was just, it wasn't, you're not actually catching dust. Okay, that would have been very exciting.
Yes, but we should talk now to Henri Rem. I think he has good news.
Yes, as you can see on the screen, we obtain with the electrons very clear waves with a period of about 1 minute. And these waves are really very well correlated with the magnetic field variations.
Well, that's fantastic. I think that's better than you had expected at this time, huh?
Yeah, we expected to have some waves between 50,000 and 30,000 kilometers.
So this comet produces a lot of waves.
A lot, much many waves than in Halley's Comet.
That's amazing. Can we actually go back to Halley's Comet for the moment? Because I find it remarkable that so many of the instruments are still working. In fact, but for what some people thought was a kamikaze mission to Halley's Comet 6 years ago, we do seem to have virtually everything still up and running. And what happened to Giotto during those 6 years, and how the European Space Agency's engineers and scientists got it here, is a remarkable story in its own right. Let's pick it up at the point where Giotto was hit by something like this.
But as it turned out, on some of the scientific instruments, data was lost for only 20 seconds. And more was obtained as the spacecraft flew out of Halley's Comet. A few hours later, when some were ready to turn it off, the spacecraft was unexpectedly given a reprieve.
We had an enormous amount of fuel left as a reserve, and this was allowed us to make full use of that to choose a target for the future.
It took half the original fuel load to correct its course to get back to Earth in 1990. But as its orbit would take it so much closer to the Sun, this would expose the delicate electronics to its heat. The top must be turned away. But this also loses telemetry back to Earth.
Once the high-gain antenna pointed itself away from the Earth on our instructions, and that's the last we saw of it until 5 years later.
In any case, there were no funds to control and monitor the spacecraft while ESA planned and costed any future mission. Nor had they any further means of checking its condition, or even how that last maneuver had ended. The final instruction had put it into hibernation. Giotto would return to Earth in 1990, exactly 5 years after launch, and 6 of its own orbits. If there were to be any future mission, it would have to be woken up and checked out several months before that. February the 19th, 1990. To send a signal to the low-gain antenna required a huge dish near Madrid, part of NASA's deep space network, and a powerful transmitter.
Attention 6-3 transmitter is going to radiate 100 kilowatts. Any objections, call 7116.
Giotto was over 100 million kilometers from Earth. At the speed of light, the signal would take nearly 6 minutes to reach it, and they must wait another 6 for it to return. But then came Giotto's faint response.
And that was wonderful. Everyone thought, well, we're there, but we were by no means there, because that just told us that the spacecraft was somewhere out there, where we thought it was. It was not yet ready to speak to us.
The next stage would be to see if it would accept commands, so it could be turned to make the high-gain antenna point back to Earth. In response to their commands, nothing. But each major system had a backup, so for 4 days they worked systematically through the failure modes. Help in diagnosis came from an unexpected quarter. Because of the damage, Giotto is not perfectly balanced on its axis. It wobbles a little. The tiny low-gain antenna on the tip, which was all they could use at this point, rotates in a small circle, and this makes the frequency of any signal broadcast from it wobble too.
This turned out to be an amazing piece of information. We could use this wobble in the spacecraft, which related to a change in the frequency in the downlink signal, to see whether or not the spacecraft had changed its spin rate or whether it was maneuvering or not.
We knew we had a spacecraft. The only thing what we didn't know at that time is, could we switch it on, could we turn it around such that the high-gain antenna would point towards Earth to allow full communication.
During the reactivation operations, it was a mixture of frustration and almost elation at every small success in the steps towards the final reactivation. So over a week, most people went through a complete range of personal feelings about the mission.
Yes, our strategy had eventually almost exhausted every possibility for success. We had been unable to maneuver the spacecraft, unable to activate the D-spin, which is the device which keeps the high-gain antenna pointing in the same direction even though the spacecraft is spinning underneath it. The next leg of the strategy said, okay, we'll make a total reconfiguration on board the spacecraft and select another power supply unit and then do the whole thing again, which is what we did.
Again, the Deep Space Network dish near Madrid sent the signal. The reply, when at last it came, went first to NASA JPL in California.
We predicted a change in a ripple on the signal, which we were expecting, a change in the period of that signal. And JPL produced a fax of this signal and sent it to us, and there was some delay whilst actually somebody at JPL had to join up dots on this fax to produce a continuous curve which we could then analyze as soon as the fax arrived here, and it showed exactly what we had hoped to see.
They now had control of the spacecraft, but were in for their next surprise as they checked its condition. A mass of red on the screens. Giotto was far hotter than expected, which may have been why 1 hour later another unit failed and also had to be switched over to its spare. At the top of the spacecraft, heat from the sun was reaching vital communications equipment. To protect that, commands had to be sent turning the top away from the sun, which meant they had to delay checkout of the scientific instruments until Giotto was further out on its orbit and getting much closer to Earth.
I don't know if you remember from last time, we had pages and pages of red. Now we're back to very, very few red, which means that's the temperatures have now cooled down.
May 1990. Several instruments have now been checked out, and here it's the camera team, housed for the purpose in portable cabins. The camera is the most complex single instrument aboard the spacecraft and potentially the most rewarding. If they can get a picture, ESA's decision to continue will be much easier. One problem is sorting out any real damage to the camera from faulty reporting or commands that are not acted upon.
The mirror commands has not been executed properly.
But at least the camera has been made to turn so that it can, in principle, find a target.
What to do next?
One maneuver does produce a clear result. When they turn the camera backwards to shadow part of the solar panel, that should result in a tiny drop in power. But there's no drop in power, so the baffle must have broken off. That's not vital, but there must be other damage too, because although the camera itself is still producing a signal, there is no clear image. This should be Jupiter.
There's camera mode again. This is on the nominal position, the nominal separation angle.
Final diagnosis, the aperture is blocked in some way.
Well, we're 16,872 kilometres from the comet, and there's 20 minutes to go. And we've just picked up news from the scientists that Chantal Levezer-Rigaud over there has picked up some interesting details with her OPE experiment. Johannes, over to you.
Did you really detect some dust already, Chantal?
Well, in fact, not yet dust, but already gas. For 10 minutes, we have already been flying inside the gas coma, and we see it very well from the CO+ data. So that's quite exciting. We are really in the comet.
So there's carbon monoxide there.
Yeah, still quite
very interesting.
Chantal, do you reckon you're inside the bow shock?
Well, no, we can't from the preliminary data we have, but we'll find something later, but obviously we have the data to find it.
Right, okay. Let's go and talk to Tony and see if he's picking up anything at the moment, just to see if I can confirm the rumour in my headphones about, 20 minutes ago that there was dust. I still don't know. It was about bow shocks instead, okay. And I wonder if Alan Johnston is picking up anything at all with his pickup irons. It is, fine, we have Alan Johnston now. You meant Alan rather than Tony, didn't you? Yes, absolutely. Alan.
Yes, well, the news is we're just crossing the bow shock at a distance of about 15 to 18,000 kilometers from the nucleus, and it's a much cleaner and much more well-defined bow shock than we ever expected to find here. So if I show on the plot here, you can see that the density is suddenly shooting way up, and the velocity is now starting to go right down. And if we look on the other displays on the next one, we can see that the distributions have broadened right out so that they've got a lot hotter, and that is a very good sign that there is a proper shock wave there. So we're finding this particular piece of transition here is one of the most interesting that we've ever seen, I think.
Very good. And it's further out than was anticipated, huh?
Yes, it's about 3 times further out than we had expected from this morning's measurements.
Does that mean there's more gas? Or?
Well, there does seem to be more gas here, yes. The gas that we're seeing here now is much more dense than we would have expected on this morning's measurements. But one of the reasons for that could be that the comet has brightened up in the last few days.
Alan, can we come back to you later on that? Because it is thrilling. It's just that I have to say that after Giotto came out of hibernation 2 years ago, the combination like yours of instruments for studying the plasma was a major factor in the decision to carry on with the mission. And in fact, scientists' instruments no longer worked. We're actually amongst those who wanted it to go on. In fact, it would be much cheaper than a mission for which a spacecraft had to be built and tested and launched. And in the end, the European Space Agency didn't have to go through the diplomatic nightmare of trying to collect new money from all the member states. As Giotto headed serenely towards the Earth, they had the decision, the funding, and the target. What they needed next was a sharp change of direction to reach it. This would be another first for Giotto.
For their course change, they planned to fly so close to the Earth that its gravitational attraction would swing it into a completely different orbit, farther out from the Sun.
If we had made this same correction using fuel alone, we would have needed 50 times as much fuel as Giotto was then carrying.
July the 2nd, 1990, 5 years to the day after launch, and 23,000 kilometers over Australia.
And in Australia at the time, it was night, and we were hoping that astronomers would be able to see a pinpoint of light. We were also hoping that it would be picked up by radar, but in the end, nobody saw Giotto flying past the Earth.
No reports.
No reports, only negative ones.
The next stage of Giotto's journey required a much improved diagnosis of the damage to its thermal insulation. It was clear that on its new orbit, further from the Sun, Giotto would get very cold. Could it survive this new peril? Its batteries had been designed to last only through the Halley mission, and the only source of power on the spacecraft is the solar panels. These had survived Halley, but now, much further out, they would no longer provide enough power for continuous operation. So, once again, Giotto was put into hibernation. This time, there was no choice. Meanwhile, its intended target, Comet Grigg Sjkellerup, was also out of sight, on its way back from somewhere near the orbit of Jupiter. It approaches the Earth's orbit every 5 years, and last time, in 1987, from Colla Alto in southern Spain, their big telescope took a picture of it when it was near its closest to the Sun.
Oh, that's a picture of the comet showing an extended coma of about 150,000 kilometers diameter. It doesn't develop a tail, but this seems quite interesting for this extended Giotto mission to have two different comets. First, the Halley, very prominent, very bright, and now this faint object. Hopefully, one can learn more about the inner part of the coma of a comet which has less activity than Halley.
Because even then Grigg Sjkellerup was on the list of Giotto's potential future targets, the telescope tracked it across the sky so its orbit could be checked before it disappeared. In August 1991, they searched for it again by pointing the telescope and slowly moving it along the calculated path as they built up an exposure. It's quite difficult to spot.
Here, right here, you can see the comet. This tiny dot, a very faint image still at the moment of the recovery.
But easier to see on the printout. On a time exposure, the surrounding stars trail across the picture. Right in the middle is the comet, exactly where it should be. From now on, the orbit of the comet would be checked and recalculated time and time again.
Well, we can do better than that, because with us here, we actually have the latest photograph of the comet. Can you show us, Johannes?
Yes, this is a photograph of Grigg Sjkellerup, was really taken this morning.
Right.
At the Chile Observatory of ESO, and there's Klaus Jockers from the Max Planck Institute at Lindau, and he kindly somehow transmitted it to us.
Well, that's marvellous news. And in fact, as Alan Johnston was saying, it appears to be a little bit brighter than it was.
And of course, it's very valuable to compare the optical picture with the data we are getting.
Yes, indeed. Well, that's a marvellous picture, even though it's, in astronomical terms, 14th magnitude, which is a very, very faint magnitude indeed. Let's go back to problems with Giotto. There aren't any problems with Giotto. In fact, as I can see from the wall, it's only about 10,000 kilometres now from the comet, and it's closing fast. And so it's doing a really excellent job. Now we can see the reason for the main hazard, though still faced today by Giotto. It's what's called its orientation. Although it's still a long way out from the sun, and so to get power, the solar cell's angled flat onto it, and the high-gain antenna has to point back towards the Earth, which means it has to go into the second comet at a very, very awkward angle. Let me show you what I mean by moving across to the model of Giotto over here. And I must say that if we actually were at the real Giotto, this, of course, as you know, is the model, I bet it wouldn't look anything like as glorious and pristine like this. It would look like a car that had actually gone in, a second-hand car that had gone into a crash, covered in dust and stuff. As you know, in the first case of Giotto, it was designed to fly into Halley's comet, bumper shield first, and even then it was damaged. This time, the comet is actually flying in like this. So the instruments and solar cells are no longer protected as they were in 1986. In fact, if it goes in like this, the dust is actually going to hit them straight on, and it will get in here to the second layer of the bumper shield. So this is where Giotto is now, closing in very, very fast. And if you were actually inside the comet, looking out towards Giotto, this is the angle you'd see. There it is just here. Dust goes straight in from that side. And that's exactly what we'll see as it happens for real. And there it is. And I can see Tony over in the scientist headquarters. Tony, are you picking up any dust yet?
No, we just checked the screen. All zeros there, no dust yet, which I think is good news, although it's too early to say we'll be safe.
Well, what I find absolutely fascinating is that you were one of the first guys to pick up data from Halley. And today it's the plasma experiments, if you like, the ones that the public would find less glamorous, which are actually picking up all the exciting data. What do you think of that, Johannes?
Well, it's a different comet.
Yes, that's absolutely true. OK, Tony, we'll come back to you because we have 10 minutes, apparently, to closest approach. And you haven't revised. Obviously, you're still thinking 4 minutes to your dust particles, are you?
It's still fitting within our modelling predictions, yes.
Jolly good. OK, you stay within your modelling predictions. Johannes, what do you think of this comet? What sort of beast is it turning out to be?
Well, it's certainly too early to say, particularly since we don't know how close we are getting, you know. But what is surprising, of course, is that the intensity of the waves and the density of the ions, of the cometary ions, which so far have been mainly fragments of water, they are higher than was expected.
Is this because it's interacting more with the solar wind, or is it that the sun is more active?
Yes, we have to recheck the solar wind, but we have fairly good solar wind data before. If we get them afterwards, we can guess what the solar wind is now, because we don't know the clean solar wind now.
Right. Well,
but apparently there's more gas coming out.
Well, talking of the solar wind, Fritz is there waiting to speak to you. He seems to have some new data.
Yes, we have some interesting new data. We have now entered what is called the pile-up region. With no clear evidence for an abrupt change towards a shock or so. So we are now at fairly high magnetic fields, much above the solar wind. And this field, of course, is produced by the accumulation of magnetic flux tubes in front of the comet.
What do you think of that then, Johannes?
Pile-up region, that is to say, you see an increase in magnetic field intensity. Huh?
Yes, it's very high up.
How high are you now?
We are now at about 32, 35 nanoteslas. It's about a factor 2 to 3 above the field outside.
Yeah.
And what does that, how does that compare with the magnetic field of the Earth there? It's obviously quite a lot lower.
Yes.
Pardon, I didn't understand.
Oh, don't worry.
It's much lower.
Yes, it's much lower. Yeah. So we're picking up waves. We're now right inside the comet. If we're actually in the pile-up region, would you like to demonstrate to us, I think, on this model of the comet over here, if we come across here, let's remind viewers back at home who don't perhaps know as much about comets as our distinguished audience here, just where Giotto has now got to. Johannes, what's your best bet?
It's somewhere at the bow shock. I think we'll get more definite data about that. Now, the pile-up region, of course, is further inside, because this red volume here, we call that a cavity, that's clean cometary gas. And the solar wind cannot get into that. So the ions, solar wind ions, and the magnetic fields pile up in front of it, you know. Right. And that's what Fritz is seeing.
And this, in fact, this yellow here actually indicates the magnetic fields inside the comet. And that's the true interior of the comet, where you don't have any magnetic fields.
They pile up, and at the same time you get bent, and that's, of course, very important to understand the processes which go on to measure the details. This is just a prediction.
Well, I think it's truly remarkable that we're getting such good data back from a space probe that's battered and crippled and has really gone through it. It's amazing stuff. And as I come back, I can see Alan on the screen. Perhaps, Johannes, you'd like to talk to Alan and see what his latest data are.
Yes, Alan. So you mentioned the shock is very sharp, and that you can confirm? Or?
Yes, we can. It's developing even more now, and if we look at the distributions here on the screen, we can see that they're spreading out very widely.
Yes.
And so the temperature of these distributions is increasing very rapidly. And it all happened at about 1510. And that would be roughly about 18,000 kilometers from the nucleus. So it seems to me it's a much more well-defined shock than we'd expected. There's some very interesting data from the combination of instruments on the spacecraft, and it's much more different from Halley than we expected.
Is this going to make your life any easier in saying what is a typical comet?
No, but we're not looking for an easy life that way. It's certainly going to be very interesting to analyze the data. And I think we'll be able to do some excellent work on it.
That's great. Now, is there anybody else in the science room who'd like to come and talk to us and tell us what they're up to at the moment? Because there are 6 minutes and 10 seconds to closest approach, 5,000 kilometers to go, and closing quickly. There we go. The lady, by the way, that you can see at the moment, who's trailing a microphone and desperately trying to get hold of scientists, actually used to be a champion sprint runner for her county back in England. She's very good at persuading people.
Here's Henri Rem.
Yes, as you can see again on the screen, we have fantastically large waves, and beginning at around 1510, and we think this is the beginning of the very large shock. So the beginning of the shock is about 70,000 kilometers from the comet.
And so that agrees with the ion data, huh?
It's electron data.
Yeah, but I mean, ion data show the same distance.
Okay.
Yeah.
Before, we have an increase in the electron fluxes, and we think this is a foreshock.
Can I just interrupt for a second? I'd like, Johannes, if you could just talk us through exactly what we're seeing on the screen for the viewers back at home.
Yes. In the top one, you see the density of electrons. Electrons are the smallest members of the plasma,
yes.
Very evasive, and has the only experiment which can detect these electrons.
Right.
And he just explained it's rising with time, and the lower panels show very intense waves, and that's at the point of the shock waves, and that's exactly at the point where Alan, with his iron instrument, sees also the shock waves.
They've all confirmed each other's results,
yes,
in a way.
Excellent.
I wonder how Susan McKenna-Lawler's getting on, or is she too busy to talk to us at the moment? Susan, would you... Chantal, oh, Chantal, yes. Hello. How are you getting on?
Well, nicely. We have been observing the dust since quite a few kilometers or minutes, I don't know what it is anymore, but
4 minutes to
we
go,
were
Chantal.
in the dust clouds at about 20,000 kilometers from the nucleus.
Oh. And what do you see exactly now?
Well, now we see a significant increase in the dust signals, and as you know,
so,
we try to find the missed distance from the shape of the curve.
Chantal, what I don't understand is if you're detecting some dust, why isn't Tony McDonald getting anything on the DIDS?
Well, I think we don't see the same level in size of the dust grains. The ones we observe are certainly much
You see
smaller.
the small grains mainly because you have an optical experiment,
Yes,
and he sees the impact. So.
Yes, and he's going in at the wrong angle as well, isn't he? He's going in at a slanted angle. Well, it's now 3 minutes and 15 seconds to closest approach, 2,700 kilometers to go. It's like one of those planes you travel on where it keeps on telling you where you are and when you're going to reach your destination. Except here, remember, we're out in space and we're 214 million kilometers from planet Earth. It's very exciting news indeed. We, I gather, are going over to Susan McKenna-Lawler to see what Epona has picked up. There she's gesticulating. She's gesticulating even before she has her headphones on, so she's obviously finding some interesting data there. I know that the red trace that she detected yesterday was much higher than she was expecting for the number of active particles around the comet. Can she hear us at all?
Hello, Heather. Yes,
Hello there,
can.
Susan. How are you getting on?
Well, I'm rather surprised by what I see here. I have traced, we're plotting omnidirectional counts in channel 1 of our telescope 1, and we're seeing rather dramatic fluctuations there. We have a rise in counts close to the bow shock, and then an oscillating behavior. And I don't know what it means at the moment. We're just recording it.
Do you think you're in what is called the mystery region that was detected at Halley's Comet, where people just couldn't explain what was going on?
Well, there's a mystery region that is rather far out that Henri Rem talks about.
Yes.
There's also the great burst of particles that Epona detected in the cavity near Halley's Comet, but I'm not at all claiming that what I see now has anything to do with that.
We'll let you get back to work, Susan.
All right,
You're obviously doing a grand job in there.
All right.
Yes. We're going across to Tony McDonald now, who I hope has picked up some dust. If he hasn't, I guess the sweepstake is off, so if you put your bets on it, never mind. Here we are, Tony. Hello, Tony. It's Heather here. Have you picked up any dust yet?
No dust events yet, and it's minus 2 minutes, so...
It is indeed. It's minus 1 minute, actually, 1 minute 15 seconds at the moment.
Okay.
Do you find that very strange, or do you think the particles are much smaller than in the case of Halley's Comet?
Well, we don't really know whether the comet is really turned on or not, really active with regard to dust, although it's been visually much brighter.
Yes, so presumably a comet can give out a great deal of gas, but it has to be rather churned up to start, as it were, getting its surface ablating as well.
Yes, indeed. On Halley, you see, we found that there was a tremendous number of large particles. Now, we are hearing from the optical experiments that there may be some small particles scattering the light,
yes,
but no
we've heard
big
that
ones
from Chantal. Okay, well, thank you very much for talking to us. We have 40... Yes, we have a very, very short time now to encounter, as you can see from the countdown on the big screen just there. I hope we don't have the same situation as we had at Halley's Comet, when the screen wobbled and went blank. In this case, I don't think we're going to. And what is your feeling about it, Johannes?
Well, in a way, if they're not big dust counts, the chances are pretty good, I guess. But of course, there always can be a single one, you know.
What about gas jets? Could that be a problem coming from the solid nucleus?
Not the gas, but the gas jets take dust along.
Yes.
And the dust is the dangerous thing, you know.
Well, here we... 2, 1, 0. Tony, we're at the comet. We've passed it. And where's your dust?
It's a clean comet.
It's a clean... Well, I'm delighted to hear. Obviously, it's a green, environmentally friendly comet that isn't chucking dust all over the universe. So maybe we hope to... Let me go over, if I can, to the flight dynamics people, the engineering...
An event!
Yeah, well, an event!
Yeah.
Yes.
We have a dust in.
We had one event. Would you, Tony, can you still hear me?
Yes, indeed. We can publish a flux curve now rather than... really very significant.
I would like to suggest that it's probably small number statistics and no one would actually believe you. Presumably, you couldn't even estimate at the moment just how big this event was.
Oh, we could do a lot of statistics with the second event.
Great.
Oh, good. Second event.
Why are you picking up dust when you're actually beyond the nucleus? Does this...
Well, the predictions did actually say that if we're going to look for big ones, there would be big more after the encounter rather than before.
It's okay.
But of course, we do have that uncertainty of encounter time. We don't know that yet, really.
Yes. Right, let me backtrack again to all of you viewers who are watching at home and wonder what on earth an event is. I do agree, we haven't explained what we mean. What we mean is that Giotto has been hit by, I think at the moment, is it 2 or 3 particles? That might not sound very exciting, but for a completely dust-free comet, for the Giotto probe to collide with bits, it's very exciting news. It means that as well as all the waves and gas we found pouring off, there really is a solid comet in there with a solid nucleus from which bits of dust are boiling off. And can I come back to control room? How many dust events have we had so far?
It's either 2 or 3.
It's
We're
either
not sure
2.
yet, because they may have been too close together.
It's 4 on the display.
In fact, there's a count of 4 possibly. We have to confirm those yet, though.
Fine. Johannes, how do you feel about this?
Yes, it's amazing, but as Tony was saying, we seem to have, there must be some dust,
yes.
Very fine dust, and rather few bigger particles which he detects.
Yes.
So the grain size distribution, as we call it, the relation between small and big dust may be different from that in Halley.
Is that because Grigg Sjkellerup is a much older comet that's tramped around the solar system many more times than Halley has?
I think this is one of the things we have to find out. If older comets, I think in this respect, what grain size concerns, there are probably many different comets, you know.
Well,
but it could be connected to that, yes.
Well, we've had 4 events so far, and those events actually came post-encounter rather than pre-encounter. Now, is that because Giotto is going into the comet at a different angle from when it was going, as it were, sort of end-on to Halley? What do you think the reason for that is?
Yes, first of all, of course, we don't know the moment of closest distance better than a minute, so maybe it was a little delayed. That would be very interesting if we can find that out. And then, of course, this is statistics. And finally, the emission of dust is not uniform.
Could it well, as you say, it could well be that we actually passed closest approach a minute later when Tony got the maximum of his
Of course, with 4 counts, I wouldn't say that. If he would have 400 counts, he would immediately be able to say that.
Don't tell that to Tony McDonnell. That's what I can say. I would like to go across to flight dynamics if I could. Yes, I'd like to talk to Howard Nye. He's sitting there waiting. Howard Nye, can you hear me?
I can, Heather, yes.
Yes, are you okay? Are you okay to talk to me at the moment?
I can say something quickly, yes.
You can say something quickly. What do you think about Tony's dust events? Does that prove that maybe closest approach was a minute later than we thought?
That's perhaps the case because we only observed on the ground here some effect on the spacecraft. We're seeing the spacecraft wobbling a little bit.
You are?
We are, yes, and the spin rate has increased by 0.01 of an RPM. The predictions that were made before the encounter said that the spacecraft could speed up during this encounter, and it did very, very slightly.
Right. And what sort of angle is it wobbling by? It's not causing serious problems for communication, is it?
It's very, very small. In fact, if you look at the display over here, you can see the wobble.
Oh, yes, I'd like to see the display, please, if you could bring it up for us.
The wobble is very, very slight here.
Oh,
it's very, very small compared with what we saw in 1986.
Right. Well, thank you very much indeed. I I hope we get back to normal, but it doesn't look like a serious problem at all.
Absolutely.
I gather we're now going to Fritz, if you'd like to speak to him.
Fritz, can you hear us?
Yes, I hear you.
Did they notice that?
Fritz Neubauer?
Oh, they picked it up on that.
He's staring at his waves so avidly. I don't think he's heard you, Johannes. Johannes wants to speak to you, Fritz.
Pardon?
Ah, pardon. Fritz, can you hear us over in the studio?
Yes, but not very well, I must say.
Okay.
Maybe why don't you just explain what you are seeing now?
We are now seeing a retreat from the comet. We are on the outbound path, and during the encounter, we have apparently not passed through the cavity because the magnetic field stayed up fairly high, so we must have passed really at a longer distance, a distance more than 100 kilometers from the comet.
And how high was the highest pile-up field strength?
The highest field was about 70 nanoteslas.
And you would expect something like 80 to 100 at the maximum? Or?
Well, we had expected a little bit lower, but the field a little bit lower, but the interplanetary field was particularly high in this case, so it's about the ratio expected.
And does that mean we were rather close to the cavity?
Yes, we must be fairly close, but we haven't really gone into it.
Right, you haven't gone into how close you might have been.
The structure is relatively complicated compared, for example, with Comet Halley. The structure is fairly complicated, so we may have some other things in the data.
Fine. Thank you very much indeed, Fritz. In fact, we've moved across now to flight dynamics, where I can see Trevor Morley being wired up for sound over there. Trevor, I understand that the drop-in count rates with the DIDS experiment might not have been due to the fact there wasn't a lot of dust around, but that your link with the Deep Space Network with NASA was faulty. Is that true?
No. What we are seeing is that immediately after Tony reported his dust impacts, that the spacecraft started to wobble very slightly.
Right.
And also we saw a very small change in the spin rate. And both those things that we are seeing are consistent with being struck by dust.
Right, so in fact, I'm sorry I mean, the DSN is wonderful, so I will not knock it at all. How close do you personally think you got to the nucleus? Have you got any hunches about that?
My hunch would be within 300 kilometers, but I wouldn't like to bet a lot of money on that. And hopefully we will find out later on after all this data has been examined.
No, we'll find out in real time this afternoon if anyone's going to push anything through their pocket computer.
We could ask Chantal.
That is a good idea. And in fact, if we pass 300 kilometers, we actually have then passed closer to this comet than we actually succeeded in flying towards Halley. I think that's incredible for a space probe which is blind, disabled and crippled and can only see, hear and smell. Now we're back, I gather, back into the scientists. There is indeed a pocket computer. I don't know what they're doing with it. Maybe they're calculating the distance as I asked them to. Johannes.
Well, the only thing we can say right now is that we were quite close to the nucleus. It just seems to me we were closer than 200 kilometers from the nucleus.
So you keep calculating and tell us more exactly later?
Estimating it just right now, but it was quite close.
Yes, very good.
Well, that's pretty amazing stuff, isn't it? To fly, I mean, it's a triumph of engineering, and it's a triumph to actually get the scientific data back, because we've heard how complicated that is. First of all, orientating the spacecraft, and then getting the experiments working again. I also feel what I find amazing about this whole mission is that the spacecraft was switched off and in hibernation for 5 years. No one was talking to it. If I was told to go into hibernation for 5 years and no one talked to me, I'd feel pretty put out.
Yes.
Is this a way of cheapening space missions? Is this a way of possibly not keeping in contact with the probe all the time?
Well, I think it's a very interesting experiment in this respect, that if you have nothing to measure or nothing particular to measure on your way, of course, it's a cheaper way. And the reawakening of Giotto is, as you mentioned earlier, a very particular feat. And I guess that other space agencies and other engineers will look very closely and say, maybe one of these days we can use this technique and save money and power, you know.
I hope so. Let us set some of these ideas in context. What I'm going to do now is to wander over to the Giotto model and show you some of the experiments which have really performed so brilliantly this afternoon. And we're very, very proud of Giotto. Just to remind you, although I'm sure that many of you in the audience don't need reminding of as to what Giotto looks like, we have the camera, which of course, unfortunately, does not appear to be working at the moment. And it comes by painfully slowly, but I will, while we're standing here and waiting for various other experiments to come around, up on the boom, which holds the big high-gain antenna that you see, that sort of bucket shape there, we have right by my hands the Fritz Neubauer's magnetometer experiments, which have picked up such amazing stuff this afternoon from this comet, have detected these enormous waves of 1,000 kilometers out in space. This is part, I believe, of the Johnson plasma analyzer sitting in there, tucked in behind there. And here we have the experiment of Giotto, which is not working on this approach simply because, as you can see, the tube is not at the correct angle for hitting the comet and the dust to go up the tube, as it were. And as we carry on, I think this is probably going to take too long to show you all the experiments. If this was the real Giotto, it would make my life an awful lot easier, because Giotto actually goes around 4 times a second. This Giotto processes in a rather gradual way. Well, at this point, I want to introduce one of the youngest guests today. I'm going down to find him over there. If you recall, back in the old days, back in the 1986 encounter with Halley's Comet, and I'll follow down here. Back in the 1986 days of the Giotto encounter, we had a terrible problem of knowing what had happened when the pictures suddenly stopped coming. And those of you who saw the programme back in 1986 will remember that there was one young man in the audience who looked at the pictures and he said very clearly to the presenter, "Mister, I think it's busted," which, for those of you for whom English is not your first language, means, "Mister, I think Giotto has been hit by something." And all the scientists who were watching in Greenwich pooh-poohed him and said, "Oh, no, of course it hasn't." But he was right. And I'm delighted to introduce Lee Sproats.
Hi.
How do you feel about today?
Very interesting results indeed.
And now let me fill in a bit of background. Lee, you have now become an astronomer yourself, a professional astronomer.
Well, not yet.
Not
yet. Degree.
You got your
degree.
degree. And what sort of degree did you get?
Astronomy.
And where was that from?
At University College London.
That's tremendous. And where are you going after you've got your degree? So you're going on now to do your PhD. I understand, ladies and gentlemen, that Lee actually just failed to get a first-class honours degree by 2 marks.
Just about.
Never mind, I only got an upper second as well. Where are you going to do your research?
Hopefully in Mullard Space Science Laboratories in Holmby St Mary to do cataclysmic variables.
Cataclysmic variables?
Yeah.
Well, it's a long way from comets, but you will be a near neighbour of Alan Johnston, of course, who works at MSSL as well.
Just about, indeed.
Tremendous. Congratulations, Lee.
Thank you.
It's nice to see you at the second encounter of Giotto with another comet, maybe a third time.
Possibly.
Okay. Thanks a lot. Well, wandering through again. And I'm going to go back to Johannes Geis now to find out if we've got any updates on what's been going on, to see if, thank you very much, to see if Tony has got any more particles. Johannes, what's the latest? Do we have any more news?
Yeah, all the experiments want to talk. Maybe we talk first to 1 or 2 of them, which we have not talked to. There's a radio science experiment.
Yes.
Let's see if they see a shift in velocity of Giotto, you know. Last time was a very small shift, and we would, of course, expect it's even smaller this time.
Yes.
But let's see if they really can detect this shift.
Right. I understand that Martin Penfold is actually waiting there. Yes, I can see him on the video screen.
Yes.
Johannes, would you like to ask him?
Yes. Have you seen what is technically called the Doppler effect? In other words, some small shift, or have you seen the wobble?
What I can say now, what my colleagues told me from JPL is that we detected a Doppler shift.
Ah, yes.
Coinciding with the time with the first dust impact. And we have a slight notation.
Yes.
That's what I can tell you now.
So that must have been a big impact, no? The first one.
It might be a very big impact, yeah.
Well, that's
Thank you. Yeah.
It's exciting to think that a comet which has got such low activity can actually produce this kind of effect, and also maybe it tells us we really have gone quite deep into the nucleus, or quite deep into the coma of the comet. Have you heard if anybody's picked up the mystery region, which we heard so much about at Halley's Comet, the region where there's no pressure, nothing much going on?
I would guess, but we can ask them, this mystery region, of course, is turned up as Halley, and it may be different in every comet, and it's because it's mystery region, may be difficult to identify so fast, you know.
I think at this point of the programme we ought to address ourselves to the problem of what's going to happen to Giotto after this encounter, and maybe after we've talked to Tony McDonnell we can go on to that. Yes. Tony, I see you've been wired for sound. Do you have anything to report?
Well, yes, the four particles we did detect were very large ones.
Yes.
So there's a lot of mass about, but it does seem to be in the big ones.
Right. What sort of mass would you estimate, first off?
Well, we're talking about probably 0.5 millimeter for the very biggest one, which might have hit the whole of the spacecraft. Perhaps a little bit smaller than the ones actually hitting our sensors, but quite a big particle, perhaps.
Thank you very much, Tony. I can see that Howard Nye is available in mission control. Howard, I think it is safe to say we have definitely passed Comet Grigg Sjkellerup now. We're out of the woods. And can I ask you, what are the plans to, what are you going to do with Giotto now?
Well, we have a plan which we use on Monday, which is to do a large orbit correction maneuver to take it onto another flyby past the Earth in 1999.
Can't you put the space probe down? Poor little thing.
Well, it seems to be indestructible. It's been past 2 comets, and I think the comets are probably coming off worse for wear than the spacecraft.
I think that's absolutely wonderful news. Do you have enough fuel left for this maneuver?
We have certainly enough fuel to do the orbit maneuver on Monday,
Yes.
and thereafter we'll have very little fuel afterwards. We have to see what we can do with it.
And what do you feel about after, when it comes back to the Earth in 1999 and makes a swing by? Are there any plans, informal plans, that you might be able to tell me about now?
Yes, we're looking at potential targets, other comets, which would be reachable with the minimum fuel and under the conditions that Giotto has to have in order to meet comets.
That's phenomenally ambitious. I really wish you the very best of luck with that plan. And wouldn't it be wonderful if, like in the 19th century, we had a really great comet coming by at the end of this century that would just put itself right on Giotto's path?
That's right.
Well, let's pray for that one. Thank you very much indeed. What would you think of a plan? It's an amazingly brave and audacious plan to send it to another comet.
It behaves very well. At the same time, there's some surprise, like this one big particle, you know,
Yes.
was as big, probably as the biggest hit by Halley, you know. I suggest we go back to the plasma and fields experiments and make another round, including Hans Balziger's experiment.
Yes, indeed. Well, in fact, what about the comet itself? What about Grigg Sjkellerup? It's an old comet. It's obviously losing matter as it goes around the sun, both gas and dust. How long would you estimate that Grigg Sjkellerup has to exist anymore?
I wouldn't know, but it's not a matter of hundreds of years. It's much longer. And but I wouldn't know how long. It will probably go less and less active. But today it was fairly active.
It was very,
in terms of gas.
put on a good show
gas.
for us.
Yeah.
I can see that we have Alan Johnston and his... I can see a finger pointing at a screen, looking very excited. Alan Johnston, are you picking us up there?
Yes, I am.
And what are you finding?
Well, we're starting to see the structure on the outbound leg now. And as far as we can see, it's following the same sort of structure as we found on the inbound. It's too early yet to say whether there will be any strong asymmetries, but again, I think you can see, perhaps from this plot here, that goes through the point of closest approach, that there is a great deal going on. It's a very dynamic situation, and we see in the middle here that the speed of the ion slows way, way down and almost drops off the bottom there. And then it comes up again on the other side.
That was at closest approach. Huh?
That was the moment of closest approach, yes.
So would you say we were rather close to the cavity in this case?
I think we could well have been, but I don't think the data I've got here will be absolutely conclusive on that.
Yes.
I understand that all of you are going off this weekend to a retreat where you're going to have a first stab at your data in some secret castle in Germany. Is that right?
Well, some people may be, but unfortunately I can't. I'm heading off for a conference in the US next week.
Oh, dear. Oh, some people have to suffer, Alan, but you've obviously got some good data, so I'm not sorry for you at all.
Yes, we've got some excellent data, and I think the fascinating thing is that it's so different from the data we got at Halley.
It's going to make life much more difficult for all you cometary scientists, though, isn't it?
It'll keep us in business for another few years.
I'm delighted to hear that. Well, what do you think? What sort of comet is this, Johannes? So, generally, what do you think?
It seems to be full of gas and not so much dust, but fine dust. So maybe we should go back to Annie Chantal and see what she has.
Yes, is Annie Chantal there? Annie Chantal's experiment, of course, looks at the dust halo, looks at the glow of...
Yes,
in
it's an optical experiment, so she looks at the whole amount of gas which the light penetrates.
Annie's there. We go to her very quickly.
Yeah.
Annie, anything to report, but very briefly?
Well, we confirmed that the missed distance was certainly smaller than 200, 250 kilometers, and that the closest approach took place a little after 1530 by 1531 and a few seconds.
Thank you very much, Chantal. Anyway, all we've seen and all that's been discovered today will, even though it's amazing, be only another modest step towards what we'd really like to know about comets. Sadly, one future mission to fly alongside a comet and watch and measure how it changes as it approaches the sun was cancelled by NASA earlier this year to save money. But we're still hoping for a future joint mission in which ESA joins once again with NASA that could be even more ambitious. It's called Rosetta.
ESA's Rosetta is designed to land on the nucleus of a comet and collect samples of the crust, minerals, organic materials and ices. It takes a core from beneath the spacecraft, collects some from the surface around it, and seals them away in deep freeze for the journey home.
I can see Gerhard on the screen just there, and in fact, Gerhard is actually wearing two hats today. There's a great celebration going on in the background there. What are you lot up to? Gerhard, as well as being the project scientist for Grigg Sjkellerup, you're also involved in Rosetta. Why do you want to go and snatch a bit from a comet?
Yeah, I think after we have experienced and really could celebrate this textbook encounter today, the second encounter of Grigg Sjkellerup, now we should go a step further and bring back material from a comet nucleus, that we could do a really detailed, in-depth chemical analysis of the most primitive matter in the solar system. And, you know, we had a lot of scientists here from all over the world, and I think we should take this opportunity really to promote a comet nucleus sample return mission that should be done by all the agencies together to bring this material into the laboratories where we could adjust our instruments to what we will get, and not that we have to develop the instruments 10 years in advance and then we'll get all the nice surprises. I think we really should go for an international collaboration on that and really go to this next step after these wonderful Giotto missions to the comets.
Absolutely, I could agree with you entirely. In fact, talking of international collaboration, I understand that in the audience we have the new administrator for NASA, who is sitting over there with the spotlight on him. Daniel Golden, I'm delighted to meet you, and congratulations on your new post. What do you think of the mission today, and do you want to go and ride on Rosetta?
I'd like to ride on a shuttle.
And so would I. I'll join you there. Thank you very much indeed.
You're welcome.
I also understand that in the audience we have Alek Galayev, who's the director of the Cosmic Research Institute in Moscow. I thought you were over there. You're hiding from me. Okay, fine. And I noticed that you are wearing a Halley's Comet tie.
Comet is unidentified, actually.
It's an unidentified comet. Now, talking of international collaboration, you, I understand, in Russia have a mission coming up next year?
Yes, we have solar terrestrial physics mission,
right?
Interball.
And you also have the Mars mission, I gather, where very many of the scientists from this mission have experiments on board to detect plasma.
Yes, that's true that in our Mars mission we cooperate with a lot of our colleagues from Europe.
That's it. Thank you very much, and good luck with your upcoming missions. It's a very exciting time for space. Well, today's encounter between Giotto and Grigg Sjkellerup has really cast fresh light on all the discoveries that brave little space probe made at Halley's Comet. We can see those findings in a new light. Now we have two comets to compare. You've heard all the scientists talking about that. But this is really just the beginning. There's so much work to be done, both for the scientists working on Giotto's findings and for those who will use the data to plan missions for the future. Johannes, as a scientist who's been involved in so many space missions, what's your verdict on today's exciting goings-on?
Well, first of all, it's obvious it was very successful. I think the Grigg Sjkellerup comet has behaved very well. Was few dust numbers, but still is exciting enough. We got some wobble and so on, so we had to tell something. What was really surprising is how good the data were concerning the dust and the plasma.
I couldn't believe that myself. I hadn't expected them to be so clean.
Yeah, so the experiments worked very well. And at the same time, we have 4 or 5 experiments. We haven't even talked to all of them.
Yes.
The iron mass spectrometer of Hans Balsiger, for instance, has also picked up the water ions.
Oh, now that's exciting, because we've spoken to Hans Balsiger, and I didn't realize he was picking those up.
So there's a lot of confirmation also. The electrons and the ions match and have to be matched. So it's a very great success. I think obviously it was worthwhile to investigate these 2 different comets. And I think, in closing, I would say it's a very good example of a European cooperation.
Indeed it is. And what a memorable event this has been to crown international space here. But it's just the beginning of several exciting projects which include trips to Mars and Jupiter, and even further afield to Saturn's bizarre moon Titan. But for me, the wonderful part of the day was the sheer buzz of a live space encounter and the amazing news that Giotto itself may be going on yet another adventure of its own. But for the moment, it's a temporary farewell to Giotto. We wish you a well-earned hibernation, and good luck to all the scientists here today who'll be going away to work on their results. And now it's time for us all at the European Space Operations Centre in Germany to take our leave of you too. We hope you enjoyed the action as much as we have. From Darmstadt, bon voyage to Giotto, and goodbye.
Well, if you'd like an illustrated booklet about that programme, please send a cheque for £2 made payable to BSS to Horizon Special, A Close Encounter of the Second Kind, P.O. Box 7, London W3